Welcome to This Explainer. Today, we're tackling something that's highly technical, but honestly, genuinely fascinating: the intricate world of directional control in power systems. If you've ever wondered exactly how engineers manage to keep the lights on when massive, city-powering electrical faults strike the grid, well, you're in the right place. We're going to break down the mechanics, the vectors, and just the sheer genius engineering that goes into protecting our infrastructure. To kick things off, I want you to imagine a scenario. You've got massive amounts of electricity coursing through power lines, delivering energy to millions of homes. But what happens when a fault hits, and that enormous river of power suddenly changes direction and flows the wrong way? Well, in an unprotected system, this bidirectional current flow can cause totally healthy parts of the grid to trip off, which cascades into massive, widespread failures. The stakes are literally incredibly high. So today, we're going to look at exactly how engineers solve this.
Okay, here's our roadmap for the explainer. We'll start with the parallel feeder problem, move into the directional control solution, break down polarizing signals and relay connection angles, and finally, we'll wrap up with the relay characteristic angle. Part 1, the parallel feeder problem. Let's dive right in. Think about a setup with a power source on one side, feeding a load on the other through two parallel lines. Now, consider a fault happening on the top feeder. The current rushes straight from the source to the fault. But because the lines are tied together at the load bus bar, the fault current actually loops all the way down the healthy bottom feeder. It travels completely backward through the bottom relay and then backward through the top relay to reach the fault. So here's the massive problem. Both of those relays are seeing the exact same fault current. Because they have similar settings, both relays are going to trip. That means the healthy bottom line gets disconnected too, and your load goes completely dark. It's kind of like shutting down an entire interstate highway system just because there's a fender bender on one off-ramp.
Part 2, the directional control solution.
To fix this, we swap out the standard overcurrent relays with directional relays, often denoted by the number 67, at those crucial locations near the load. Now, the bottom relay is specifically designed to only operate for current flowing toward the source. Because the fault current is flowing backward, the top relay trips, isolating the fault. But that bottom relay? It simply ignores the reverse current flow. The bottom feeder stays online, and the load keeps getting power. It's a beautifully elegant, localized fix to a huge systemic problem. To pull this off, engineers use a very specific setting philosophy. The core assumption here is that normal, everyday load current always flows in the non-operate direction, meaning toward the load. So absolutely any current flowing in the reverse, operate direction is a 100% guaranteed sign of a fault. Because of this certainty, these directional relays can be set to be hypersensitive, typically triggering at just 50% of the normal load current. And they can be set for lightning-fast operating times, like a time multiplier setting of 0.1. They don't need to sit around and verify. If the current goes the wrong way, boom, they act instantly.
Part 3, polarizing signals explained. Now, you might be wondering, how does the relay actually know which way the current is going? It uses something called a polarizing signal. This is basically just a stable reference voltage that the relay uses to compare against the operating current. By checking the phase angle of the current against this solid reference, the relay can definitively calculate whether that current is moving forward or backward. But this creates a pretty tricky engineering challenge. If our operate signal is phase A current, which voltage should we use to polarize it? We actually have a whole bunch of choices: phase A, phase B, phase C, or phase-to-phase voltages, like A to B, B to C, or C to A. Instinctively, you'd probably think, well, if we're measuring phase A current, we should definitely just use phase A voltage, right? Actually, scratch that. Matching phase A voltage with phase A current fails spectacularly in a real power system. During a fault, the current shoots up. And because power lines are highly inductive, that fault current severely lags the voltage. The current vector falls straight out of the operate zone and drops right down into the restrain zone. The relay would see a massive fault, but totally refuse to trip because the angles shifted so much it actually looked like reverse flow. It's like trying to use a compass while sitting right next to a giant magnet. Your reference is completely warped by the chaos around it. We need a much better reference. So here is the clever workaround. Instead of using phase A voltage, we use the cross-phase voltage, voltage BC. By grabbing the voltage from the other two phases, which, by the way, stay relatively healthy and stable during a phase A fault, we establish a rock-solid reference. And even more importantly, it perfectly shifts our characteristic. Our maximum sensitivity line is now positioned so that the highly inductive fault current lands dead center in the operate zone. The relay will confidently and correctly trip every single time.
Part 4. Relay connection angles.
We call this specific relationship the relay connection angle. It's defined as the angle between the applied current and the applied voltage at system unity power factor. That setup we just looked at, applying phase A current and phase B to C voltage, creates exactly a 90-degree angle. In the industry, this is known as the quadrature connection. Now, back in the day, engineers messed around with 30-degree and 60-degree connection schemes, but those are pretty much obsolete today. The 90-degree connection just gives far superior performance and has become the absolute modern standard for all overcurrent relays. To make sure the entire three-phase system is protected, we just apply this 90-degree logic across the board. It maps out super cleanly into this matrix. The relay protecting phase A takes current A and uses voltage BC. The relay for phase B takes current B and uses voltage CA. And finally, phase C takes current C and references voltage AB. This setup guarantees that no matter which phase takes a hit, the relay always has a healthy, stable cross-phase voltage to rely on as its polarizing reference.
Part 5. Relay characteristic angle.
Okay, so we've established our 90-degree baseline, but different power grids actually have vastly different physical properties. We have to fine-tune our relay's maximum sensitivity to match the specific grid it's protecting. We do this by adjusting the relay characteristic angle, or RCA. By definition, this is the precise angle by which the current must be displaced from the voltage to produce maximum operational sensitivity. Basically, the relay is electronically shifting its sweet spot to perfectly match the expected angle of a fault current on that particular network. Let's visualize this with some vector math. Our standard 90-degree connection puts current A 90 degrees away from voltage BC. But when we program the relay with a 45-degree RCA, it internally rotates its maximum sensitivity line by 45 degrees relative to that voltage reference. The operate and restrain zones shift right along with it. The relay is now perfectly tuned for a fault current that lags by exactly 45 degrees. Compare that to a 30-degree RCA. Here, the maximum sensitivity line is shallower. The entire operating boundary rotates to fit that 30-degree offset. By tweaking this internal angle, protection engineers can perfectly align those operate and restrain regions. This ensures that normal, everyday load variations never accidentally trigger a trip, but genuine, dangerous faults are caught the millisecond they happen. So, the absolutely crucial takeaway here is that the choice of this relay characteristic angle is not random. Not at all. It is directly dictated by the physical earthing characteristics of the power system you're trying to protect. If you're on a resistance earth system, the fault current is more resistive, so you use a 0-degree RCA. For lower voltage distribution systems that are solidly earthed, the lines have a moderate mix of resistance and inductance, so a 45-degree RCA is perfect. And for those massive, high-voltage transmission lines that are highly inductive, the fault current lags severely, so engineers set the RCA to 60 degrees. It really is a complete marvel of engineering. The physical construction of the towers, the power lines, and the grounding rods hundreds of miles away directly dictates the precise trigonometry programmed into a tiny relay box at your local substation. So I want to leave you with this thought. The next time you look at a massive electrical substation, consider the invisible, perfectly calibrated math happening inside those relays every single millisecond. How does the physical earthing of the grid right outside your window dictate the angles protecting your power? Thanks so much for joining me for this explainer. Stay curious.